Hi everyone, my name is Aditya Bindal. I'm a senior product manager at AWS. And today I'm going to talk to you about AWS Deep Learning Containers. So in this webinar, we'll review deep learning containers and the key features of deep learning containers. We look inside the Docker images and see what options and configurations are available. We look at some custom setups to use deep learning containers in real production environments. And finally, we'll do a hands-on demo with deep learning containers on EC2 and on ECS. So we launched deep learning containers in March this year. And deep learning containers are a set of Docker images that are pre-installed and validated and optimized with the latest deep learning frameworks and libraries. Now, we'll unpack what all of that means, but for now, you can think of these images as ways for developers and data scientists to get high performance container environments for their machine learning training and serving needs at scale. Let's take a step back and look at machine learning on AWS before diving into deep learning containers. At the very top of the stack, you have application services, tools like Recognition, Poly, Comprehend, and Lex, and Forecast, and Personalize. And these are specific tools in a specific domain area that allow you to quickly and easily use a pre-trained machine learning model to generate predictions with a simple API call. You can integrate these machine learning predictions into your applications and services seamlessly. Then in the middle layer, we have Amazon SageMaker, which is a fully managed service for labeling, building, training, and deploying your machine learning models, all the way from experimenting in a Jupyter notebook to deploying models in production. With Amazon SageMaker, data scientists have the ability to take models, train them on a large cluster of GPU or CPU instances, and deploy them into production environments with endpoints that scale and provide additional features such as A/B testing. Finally, powering all of these services and tools is the bottom layer. And that's where we'll focus today. So we have in the bottom layer the machine learning or deep learning frameworks such as TensorFlow, MXNet, and PyTorch. We also have additional libraries such as Gluon and Keras, and we have hardware, such as EC2, P3, and P3DN instances, and CPU instances such as C5. We also have the upcoming G4 instance type, and we have services like Greengrass and Elastic Inference. You'll find that we also offer images that package and combine all of these together. So deep learning armies on EC2 give you optimized environments for training and serving models with TensorFlow, MXNet, PyTorch, Chainer, and additional frameworks on a variety of different EC2 instance types. And what we are talking about today is deep learning containers that give you prepackaged environments for training models and serving models in TensorFlow and MXNet across these and more services and across a variety of hardware. So setting up a process or pipeline to build, optimize, test, and integrate containers for machine learning can be challenging. Customers have told us how it took them days trying to build and test a performant TensorFlow Docker image with the right versions of NVIDIA libraries and Python dependencies. And what makes this particularly challenging is the pace of deep learning frameworks and libraries innovating. This isn't a one-time investment, and it requires rebuilding, re-optimizing, and retesting new images when new versions of TensorFlow or MXNet are available. And if we step back, building performant containers is just one part of the problem. You also have to figure out scheduling, orchestrating, monitoring, and scaling your containerized applications. So working backwards from these customer problems and challenges, we built AWS Deep Learning Containers. These are lightweight, flexible Docker images that are purpose-built and optimized for training and inference across multiple deep learning frameworks, hardware types, and Python versions. With deep learning containers, customers get access to a repository with the latest and greatest deep learning frameworks and libraries validated across multiple AWS services and hardware types. Now, deep learning containers pack the same optimizations to frameworks that we offer in Amazon SageMaker, our fully managed service, as well as the deep learning armies. So when you train ResNet 50 on an 8-node GPU cluster, you see a 27% increase, which lowers both your cost to train and your time to train. On inference with ResNet 50, if you take a single CPU instance, you see a 2x improvement. And what that means is that when you use deep learning containers or the deep learning army or Amazon SageMaker, you benefit from all the optimizations, improvements, and testing that AWS makes to deep learning frameworks like TensorFlow. And these optimizations will both reduce the time to train as well as your cost to train. Now, what makes this powerful is when you combine deep learning containers with AWS container services. So deep learning containers give you the frameworks and the software and the libraries that allow you to train and serve models, excuse me. But you still have the ability to combine these images with AWS container services, such as the Elastic Container Service, also known as ECS, and the Elastic Container Service for Kubernetes, or EKS. And when you combine deep learning containers or when you use deep learning containers with these services, you benefit from all the orchestration, monitoring, scaling benefits that these services bring. And with ECS and EKS, you get access to a variety of compute and storage options, such as S3, EBS, EFS, and FSX Lustre. So to summarize, deep learning containers provide optimized and validated images for training and inference, which you can use on EC2, ECS, and EKS to set up custom ML environments and pipelines. This gives you control over your infrastructure and sets you up to scale out when you need to use multiple nodes for distributed training, or you need to scale out a cluster of CPU instances for your TensorFlow serving containers. So let's talk about what's available and what's inside deep learning container images. Our images are available via the Elastic Container Registry, or ECR, in 15 AWS regions. As new versions of frameworks and libraries are released, we update and make these new images available in the same repositories. So as you can see in this image, you always have access to TensorFlow and MXNet images. And using the tags, you can specify what versions you want and what flavors you want. So let's go into this in some more detail. We offer 16 images in each AWS region, and we have 8 images per framework, so 8 TensorFlow and 8 MXNet. And we have 4 images for training and 4 images for inference, which are then further broken out by GPU, CPU, and Python version. These images are intentionally minimal and kept separate by the hardware configuration, the Python version, and the framework to ensure that the containers are lightweight and only give you what's necessary and nothing in excess. Now let's look at what's inside our container images, starting with the GPU images. So all our Docker images begin with a base of Ubuntu 16.04. TensorFlow training and inference images include CUDA 10, and the training image includes Horovod, which is a distributed training framework that AWS provides along with TensorFlow and gives some of the optimizations and benefits we talked about earlier in terms of performance. The MXNet training and inference images include CUDA 9, and all images also include common libraries and packages used by data scientists. Switching over to the CPU images, the CPU images include Intel's MKL-DNN accelerator library that accelerates training and inference on Intel CPU instances. And it's important to note that these images do not include any GPU-specific libraries or software to keep them minimal and lightweight. So you can find additional details, including a bill of materials for all of our Docker images in our release notes. And you will also find specific versions of each of these libraries and any known issues or compatibility issues that we call out. So now that we understand what deep learning container images are available, and we know how to get deep learning container images, and we've looked inside specific Docker images to see what libraries and software is included, let's look at some example custom setups. So in this first setup, deep learning container images are deployed on a single EC2 instance that you manage, and we'll review this type of setup in our demo. So as you can see, the images are pulled from the Elastic Container Registry, and the user in this setup is using S3, the Elastic File System, and code commit to train and serve models on EC2 instances that they manage. The second setup, which really demonstrates the power of deep learning containers combined with AWS Container Services, shows how you can use deep learning container images and deploy them on a cluster of GPU instances that are managed by EKS. So again, you can use the Elastic Container Registry to pull the images. If you would like to make customizations to the image, you can push those changes back to ECR. For storage, you have an IO, you have S3 and the Elastic File System, and code commit for your private Git repository, all of which you use to build your own custom environment and pipeline on EKS. We'll review this type of setup in more detail in the demo as well. And finally, before we switch to a demo, I'd like to show you an actual customer's experience using deep learning containers. So before deep learning containers, this customer's data science team used deep learning armies to build and train models in TensorFlow. A separate engineering team then deployed the models trained by the data science team to their production environment using containers. The process of productionizing the research team's code and converting everything from the deep learning army environments to their own custom-built containers took considerable time and led to several issues that both teams had to spend cycles resolving. By their own estimate, this typically took up around 20% of the project. Now, if we could resolve the issues between research and production, we not only increase the speed to market, we are also giving the customer an easier path to productionizing and identifying production issues sooner. So now with deep learning containers, the same images are being used in production and in research training and evaluation. So what this does is it allows the data science team to catch issues and resolve issues that will be encountered in production sooner. And for the production team, they no longer need to go through a manual process of trying to replicate the environment that the data science team was using. The same Docker images and the same binaries are flowing through from research to production. So with that, let's switch over to a demo. And what I'm going to do in this demo is start by training the MNIST CNN model on EC2. And I will show you how to pull the deep learning container image and then run a training script on the deep learning container. We will then switch to EKS, where we will train in Kubernetes with EKS. We'll set up a gateway node, we'll create a cluster, and then we will train in Kubernetes with EKS. So with that, let's get started. So on my EC2 console, I've already created a EC2 instance. And I'll use this EC2 instance as my master node for running this demo. So logging into this EC2 instance, and I've already run AWS configure. So my access key, my secret access key, and my default region are already set. And now what I will do is find the right image that I would like to use. So as we discussed, the images come in 16 different flavors. And what I would like to use currently is the TensorFlow training image on CPUs with Python 3.6. So I'm going to define a new variable that says my CPU container image is the one I described here. And because we're using the Elastic Container Registry, we will log in to the registry. This is a step that's needed when you are using deep learning containers from EC2, but not required when you're using it from ECS and EKS. And you'll get a message that says login succeeded. confirming that you have access to the deep learning container registry. And now what we'll do is we'll run this Docker image. And immediately you can see that we're now inside the bash environment for the container. So we're no longer in the instance, we're in the container that's now running on the instance. And to demonstrate how we're going to use deep learning containers, we will clone the Keras repository, which has example models and scripts. And what we will use is the MNIST CNN model. So immediately you can see that it's now using the TensorFlow backend. This is the TensorFlow that's provided from the deep learning container, and it has all the other Python libraries and dependencies that are required. And we now see the training has commenced, and it's going through and training our MNIST CNN model. So while that's happening, what I would like to point out, show you is each of these images can be pulled onto an EC2 instance, and there's no configuration or tuning that's needed for you to start training or start a TensorFlow serving container and use it for inference. And just the way we bashed into the container, we can pull our models, our codes in from anywhere. So we can have a private Git repository, we could use code commit, we could pull a file from S3. And let's go ahead and stop this training for now and exit from the container. So now, as you can see, we're back in the EC2 instance. So that is training on EC2. And if you allow the training to complete, you'll see the target accuracy you reach with this model, and you'll have a trained model by the end of it. So now let's skip to training in Kubernetes with EKS. And when you train with EKS, or if you do training or inference with EKS, the first thing you have to do is set up a gateway node. Now, this gateway node could be your own local machine, or it could be an AWS EC2 instance. What I've chosen to do in this demo is an EC2 instance, and I use the deep learning base army. But you could use your laptop or your workstation as well. And we have in our documentation a step-by-step guide on how you would set up your gateway node. So for this demo, we will start with the gateway node that's already set up, and we'll start by creating our cluster. So we'll use a tool called EKS CTO, which is a command line tool that allows us to create clusters in EKS, where we can specify a name for our cluster. We can specify the version of Kubernetes we want to use. We can specify the nodes, the number of EC2 instances we want attached to this cluster. And we can specify the type of node or the instance type that we would like to use. In addition, you would specify some your SSH public key that you use to connect to EC2 instances, and then the region that you would like this cluster set up in. So for this demo, we will use a single P3 2x large instance, but as we discussed earlier, we could use any instance type, CPU or GPU, and we could set up a multi-node cluster with multiple P3 instances. So let's go ahead and do that. So I'm going to create a cluster in EKS using EKS CTL, and I will use a single P3 2x large instance, and I've provided my SSH public key, which you would replace with your SSH public key. Now, immediately what you would see is it starts creating the cluster, and you can monitor the progress of cluster creation on the AWS console. So if we go to the CloudFormation, you'll immediately see that there's this new EKS CTL Deep Learning Container Webinar cluster, which is the name that I had provided, Deep Learning Container Webinar, that gets created. And this CloudFormation template is now in progress. If for any reason you run into errors or issues, you'll always find the error message and what went wrong with the cluster creation in CloudFormation in the events panel over here. And EKS CTL is quite resilient, so if it encounters errors, it has a rollback mechanism that cleans up and doesn't leave you with a partially set up cluster. So typically this process takes around 10 to 12 minutes for a single GPU instance and longer if you're spinning up a multi-node instance. If you're curious at what's happening beneath the hood, you can look at the actual CloudFormation template that EKS-CTL creates on your behalf to spin up this cluster in EKS. The other thing I'd like to show you is in EKS, you will now see a new cluster that's been created on your behalf called DL Container Webinar. Recall, this is the name that we gave the cluster, DL Container Webinar. And you'll now see that this cluster is being created in the region you specified, and you can start monitoring it both here and in CloudWatch. So this process, as I mentioned, takes between 10 to 12 minutes. So let's jump ahead to that section when the cluster creation is complete and continue from there. Scott, so we now see that EKS-CTL has completed creating our cluster. So let's go verify that in the AWS console. So to start with, let's refresh the EKS console. And we now see that our EKS cluster is active. If we look at our CloudFormation template that EKS-CTL created on our behalf, we see that the creation of this cluster is now complete. And if we go back to the EC2 console, we now see a P32X node that has been created for us. And this is the node that's now part of our EKS cluster. So before we continue with training, I wanted to highlight two things. The first was, some of you may be unfamiliar or new to Kubernetes and EKS, and we've included a glossary and a definition of key concepts that are relevant when you use deep learning containers in EKS. So if you are seeing EKS-CTL, KSonnet, Cube CTO, Kubeflow, things like this for the first time, this document is a really good guide to getting started with Kubernetes and EKS with deep learning containers as your use case. In addition to this glossary and key concepts guide, we also have a document on troubleshooting deep learning containers on EKS. So we haven't used the deep learning containers in EKS as yet, but even during setup, when you set up your control node, you may encounter some issues in creating the cluster or in verifying that your nodes have been created. And this document will walk you through some of the most commonly encountered issues and how you can resolve them. So with that, let's go back and now use the EKS cluster that we've created to run a few more configuration steps, and then we'll be ready for training. So the first thing that we want to do is apply the kube config to our newly created Kubernetes cluster. So what we're going to use is the AWS command line. And within EKS, in our region of choice, with the cluster that we just made called DL Container Webinar, we will make sure that update kube config is run. And you'll see a message immediately saying that the context has been updated in the cluster that we specified. Now, since we decided to use a P32X large, which is a GPU instance that includes NVIDIA GPUs, we will apply this plugin from NVIDIA that is required for running GPU workloads with Kubernetes. So now we use the Cube CTO, and we'll use this Cube CTL command line tool for subsequent commands where we actually run our MNIST training model. And we see now that the NVIDIA device plugin was successfully added to our Kubernetes cluster. Now, usually this might take a few minutes, but it's a good practice to now verify that we can see our GPUs. So the command to see what nodes you have available is kubectl get nodes. And we can see that we have one node that's ready. Now, if you add this option that I've highlighted here, it will tell you that how many GPUs you have on each node. And this is showing us that we have one GPU available on a single node that we created in our EKS cluster, which is exactly what we expect with the P3 2x large. If we added multiple nodes, then we would see all the nodes here with the GPUs they had available. And if we created a node with more GPUs, we would see more GPUs when we ran this command. So the next step is to now create a YAML file for training. So the way you specify the container image and the commands you want to run inside the container in Kubernetes is by putting all of that in a YAML file that goes inside each pod. So what we have here in the highlighted section is a structure that allows you to say, create a TensorFlow training pod. And that TensorFlow training pod will take the deep learning container image. This URL is what we saw previously. And within the container image, I want to run the MNIST-CNN model by first cloning the Keras Git repository and then running the MNIST-CNN Python script. And I'm putting a limit on the number of GPUs as one, as these are the resources that I would like my Kubernetes cluster to use. And if there is a failure on this pod, then I want the pod to restart. So let's go ahead and create this YAML file. And now what we can do is create a new pod. That takes this pod YAML specification. So as soon as I hit enter, several things will happen, but let's walk through that first. So as soon as I hit enter, this pod will be created and we would have a TensorFlow training container image loaded onto that pod, and it would start executing the commands that I specified in the highlighted section over here. And once that's happening, you can verify that the pod is active, and then you can start seeing the logs from your training job to verify that your model is training correctly, and you can track progress. So let's go ahead and create this pod. And now when I say kubectl get pods, it says container creating. And so this could take a few minutes. And if you want to see what's happening on that pod, you could say kubectl logs. And it's still starting the container, so it's not ready. So we can give this a few minutes and skip ahead to the section when the pod is ready. Scott, let's continue. So we see that the pod is now running. The status will change to running and then to completed. And if we do kubectl logs and specify the name of the pod, we can see that our model trained successfully, and we will get a log output of model training, showing us the test loss and accuracy. Now that you've trained your model, if you want to spin down this cluster, all you would say is EKS-CTL delete cluster and specify the name. And this would commence a process of deleting the EKS-CTL cluster, which again will take around 10 to 15 minutes. And while this is happening, let me show you that for now, you will still see that node because it's in the process of being deleted. And the EKS status is active, but this will change. So if you want to see if your delete is in progress, you can go back to CloudFormation. And just the way we saw EKS-CTL DL container webinar cluster creation, we will see a similar step now for deletion. And the delete is in progress, and we can track the progress here. Once this process completes, we'll see the EKS cluster is no longer active, and we'll see the EC2 instance has been deleted. So to review, we started by training training on a single EC2 instance, and we pulled a deep learning container image from the Elastic Container Registry, or ECR. We ran that container, and we trained an MNIST-CNN model on EC2. And note that we use the CPU Python 3.6 TensorFlow training image. We then used EKS to train our model in a Kubernetes cluster. We set up a single node P3 2x large cluster that had one GPU. And in this cluster, we created this YAML file that specified a GPU deep learning container image. So this is a TensorFlow training image, same version of TensorFlow, but instead of the CPU version we used in EC2, we now use this GPU version. And again, we run the same model, and we see the training completes in our Kubernetes cluster. And then finally, once we were done, we decided to kill the cluster by using EKS-CTL delete cluster, which triggered a process to destroy the nodes and the EKS cluster itself. Now, we reviewed single node training on both EC2 and EKS, but deep learning containers are also built with distributed training in mind. Distributed training is when you horizontally scale by the number of nodes in your cluster, either in EC2 or in EKS. And so what we have here is an example of how distributed training would work. So on the left side, you have the same EKS-CTL create cluster command that we just used. And instead of specifying just one node, we now specify two nodes of a P3 8x large instance type. And the image we provide is the same one. It's TensorFlow training 1.13 with GPUs in Python 3.6. And we specify that we want the GPUs per worker to be 2, the number of workers to be 2, and we create a name for this job. And then we use KSonnet, which is another tool and utility within Kubernetes that allows us to train ResNet using Horovod. So this script and the step-by-step instructions are in the user guide in the URL linked below. And before we wrap it up, I wanted to share some useful reference materials as you use deep learning containers across EC2, ECS, and EKS. So we have detailed step-by-step guides and tutorials that cover training and inference with both TensorFlow and MXNet across EC2, ECS, and EKS. With EKS, you'll also find detailed step-by-step instructions on distributed training with TensorFlow and MXNet. With TensorFlow, distributed training uses Horovod, and with MXNet, we use the parameter server approach. We would love to hear feedback on what else you would like to see in the deep learning container images and how we could make training and inference easier for you. So please give us feedback and ask us questions in our AWS forum. Finally, we have customers that will take the deep learning container image as a base and then layer their own custom code and software tools and agents on top of it. So what we provide is an example of how you could take the base deep learning container image and create a Docker file that takes the latest version of our deep learning container image and then adds custom code. So that could be a model that you want to add. It could be a software package or a library that you want to add to the deep learning container image. And this is another reason why we intentionally kept these images lightweight and minimal so that you can easily add your customizations on top instead of including all options from the beginning. So in addition, we, as I mentioned, we have a glossary and key concepts guide on EKS for those new to EKS, and a detailed troubleshooting guide for using deep learning containers on EKS. And finally, if you're using the CPU containers, we have a document and a user guide with recommendations on how to use Intel MKL correctly, depending on your model and workload. So with that, thank you so much for listening. I hope you found this useful.